Bodnar, Topological Deep Learning. Thank you very much, Cristian.
Okay, hi everyone. So I'll give two talks today about this thing I'm calling topological deep learning. So this sort of started with my PhD proposal about 2 years ago. And actually, I didn't know exactly what this means, but I just used it in the title because it was about topology and deep learning. And actually, I've used this term informally a lot since then, and many other people have. And actually, it also showed up in in print or in papers more recently. And I put like some references at the bottom, or similar terms like topological representation learning. So, for instance, Bastian Rick, who's been doing lots of work in this area, has been organizing at ICLR these workshops on topology and geometry, and he called them topological representation learning. So it's something that's kind of taking off, but I think personally, until now, I never had the time to actually put it together and kind of say, okay, what's the vision of this? What are we trying to do here? And the purpose of these talks will be to kind of crystallize and kind of give this big picture and see how this big picture is realized with some concrete papers we've done. So that's kind of the overview. And what I actually mean by topological deep learning is that we're going to assume that we have a topological space and our data is attached to some neighborhoods in this space or some open sets in this space. And we'll see that this approach can get us quite far. Now, needless to say, since you're all here, you know that geometric deep learning has been very successful. And since many of you came from very far to be here, I guess you heard of some of these successes and some of the progress that has been made in these areas. That's partially to the fact that there are many applications where data resides on these non-Euclidean spaces or more interesting spaces where you have interesting geometries or they just don't look Euclidean. So you have molecules, meshes, manifolds, and whatnot. Now, I'll probably be kind of the black sheep of these talks because I'm going to kind of argue that geometry is not enough, at least not in the strict sense of differential geometry, or what we typically call geometry. I guess the thing Michael talks about with like in the Klein sense of geometry is much more general. But I'm going to argue that geometry is not all you need, and probably this should be quite clear from this diagram I was presenting yesterday. So there are these spaces that are not even topological manifolds, so you can't even talk about that. But then you would need even more things. You would need smooth structure to even start talking about geometry. So there are these things on the left side of this diagram, that these spaces that look very weird, and you can't apply geometry on them, or at least not in a natural way, or it's not very obvious how you should do that. I'm not saying it's impossible, and actually you'll see some great research this week doing that, and actually also in my talk, but we're going to take a slightly different approach. In this blog post you see below, Michael was arguing or discussing the fact that pretty much all the spaces that show up in geometric deep learning, they have this continuous manifold equivalent, and that allows you to do lots of things. So if you talk about grids, they have these planes. If we talk about some mesh, you have the underlying manifold, the mesh is discretizing. But if you look at graphs, then you have this very big question mark, like what's the continuous thing we can use there? And it's perhaps a bit ironical that graphs, which are kind of the most prevalent space in geometric deep learning, doesn't come with a natural way to actually do geometry on graphs, or is not very obvious because of this kind of question mark you have here. So we're going to see that if we actually take a topological perspective, it's very easy to fill in that question mark, and it can get you quite far. So why should we care about these things and topology in general? Well, even if you love geometry, you're going to have some dependency from the topological layer of your structures. So there are these things called topological obstructions, where simply, for instance, if you have a vector field on some kind of sphere-like manifold, and Michael was also mentioning this in the talk before, you'll have some singularities in your vector field. So there's this saying that you can't combo coconut or something like that. And this is a failed attempt because you end up with this kind of singularities at the poles. Now, for instance, another example is, let's say you do some you have some smooth function on a sphere, and maybe you want to classify points on a sphere, there is this kind of mind-blowing result called the Borsa theorem that says you're going to have some antipodal points on this thing that are going to take the same value. And this actually holds just more generally. It's not just for the real numbers, but it will actually hold for like other Euclidean spaces you put here. So if you want to classify things, you might, on a sphere, for instance, you might want to be aware of these kind of limitations you have sort of from the topological layer. Now, what we're going to do is adopt sort of the minimal structure we can assume about anything, and that's the topological structure. And that's like a universal way to talk about everything. So you don't need to, discrete or continuous, it doesn't matter. Actually, in topology, when we start with the definition of a topological space, which we'll see again in a second, but you also saw it yesterday, there's no kind of differentiation between kind of discrete and continuous in kind of the basic definitions. We just have a space with some topology, and everything kind of depends on that topology, whereas, in geometry, we already assume, okay, we start with something smooth. So we have like a very natural transition between these spaces, and that's given by neighborhoods. So we can talk about neighborhoods or open sets in any of these settings by just putting some topology on these things. So what this gives us is a bottom-up approach. So essentially, in mathematical physics, we generally start with sets, and we keep adding structures on top of these sets. So first is topological spaces, and we're going to primarily work at this level. And then, as we saw, we can kind of put extra structures. So we have topological manifolds, smooth manifolds, and then geometry, I guess, kind of starts somewhere at the top. And in general, when you have these, for instance, graphs, you'll often take this kind of top-down approach where you kind of guess, like, okay, what will be the equivalent of that on a graph? And if your guesses are good, I guess at some point you get some good results. But what we're going to do is just take a bottom-up approach, and we see we don't actually need to make some weird assumptions or guesses. Everything kind of comes naturally, and we can actually recover some of the kind of upper layer structures from that thing, from that perspective. Yeah, so that's what I've just said. Now, one other advantage that kind of topology gives you is that topological properties are kind of by definition robust to noise. So for instance, we talked yesterday how homeomorphisms allow you to express things like this, that the donut and the mug are the same thing. And you could think of all these transitions as some sort of perturbations to the initial surface. So if you think you have some noise that perturbs your surface or your space, you see that it's kind of very hard to you can do lots of perturbation. Arguably, this mug is like extremely perturbed version of your original space, but still it encodes the same topological information. So you have this kind of topological protection against these noise, and this idea actually was used in these topological quantum computers where you can encode the state of a qubit by this sort of topological information. So they have these things called braids that sort of yeah, it's just like some kind of overlapping strings, and it's very hard to kind of perturb them without, and destroy that their topological structure with perturbations. So they're very good against noise. Another thing this gives us is that it gives us a a categorical approach to data processing. So actually, category theory started in algebraic topology, and it's very natural to see why, because we can associate with certain spaces, we can associate some group structure or some sort of algebraic structure. And for instance, if these two manifolds are homeomorphic, then we also have this translates into an isomorphism between these groups. So essentially, category theory offers this very nice way to translate when we talk about some things. We talk about spaces or like some manifolds or whatever, topological spaces, about group or other algebraic structures. So that's category theory should probably be something that emerges naturally in this sort of framework. Now, we saw this already, but I'm just kind of adding it here because it's quite important. So again, the topological space is essentially just a set, and we put extra structure on top of these open sets that essentially kind of define neighborhoods for the point in this set. And as I said, one way to yesterday, one way to think about this is kind of picking a resolution to look at your space. So essentially, if you pick like a very low resolution, you end up with these spaces that we typically call discrete or that look discrete. If you pick a very fine-grained resolution, then you get something that looks smooth and continuous like a manifold. But you can see you can naturally refer to both of these things without kind of any differentiation or like without kind of being super careful or anything. Okay, and I guess one natural question is, where should we put all these things, or how should we kind of, in the grand scheme of things, where do we place all these kind of research direction? And in some sense, we could kind of look at what happened in Poincaré's paper Analysis Cities, which was kind of the official history of algebraic topology starts with this paper, in which pretty much what we're going to do in the first part of in the first lecture today is everything was done by Poincaré in this paper, which actually is a series of papers. He had many supplements to this paper, and he was very interesting because he didn't kind of believe in revising papers. So it was kind of like he had some ideas, you put it there, and you just send it to print or something. So that's why also one of the reasons it had many kind of supplements that show up later with kind of corrections or modifications and so on. But his intuition was brilliant, and even kind of the mistakes in these papers led to some interesting results. So yeah, what I want to say with this is that he was discussing about the group of homeomorphisms, which I think Maurice also talked about yesterday, or diffeomorphisms. And you could, that space kind of acts on the actual space you have, and you could think of kind of topology as studying invariants of these kind of homeomorphisms. So in some sense, he was arguing that topology at that time would be a subfield of geometry, or at least Klein's geometry in Klein's sense. So similarly, we could see these as some subfield of geometric deep learning, where now we look at invariants that look a bit more strange. So we have these homeomorphisms. Although I would argue at the same time it's kind of different, because we don't actually, the cases where we actually want to be invariant, completely invariant to smooth deformations might be something super, super strong. So, we might not use it exactly in the same way, but we might still be interested in kind of topological invariants that show up naturally in learning without being sort of explicitly coded. Yeah, so in this sense, we can see topological deep learning as some subfield or sub-research program of geometric deep learning. Okay, and what I'm going to talk about in this first part is called topological message passing, and Michael already mentioned a bit about this. So yeah, let's get started. So in graph machine learning, I would say you typically have two kinds of tasks. So the first kind of tasks are these graph level tasks, where essentially you're given a data set of such graphs, and you have some features for each node. And what you want to do is compress all this graph into a single vector and then classify that vector. So one example is if you want to predict the solubility of molecules, you would have a data set of molecules. You want to map each molecule to a vector, and then predict from that vector some number, the solubility or something like that. Now, the other kind of tasks are these node level tasks, where you have a single graph, and for instance, you want to classify the nodes, and you want to find some sort of decision boundary, and you have some nodes that are labeled, but you also have these gray nodes that are not labeled, and those ones are the ones you actually want to find what the label is for them. And for instance, one example is fraud detection or spam detection. So if these are networks of spammers and real users, you want to kind of find the spammers. And we're going to see today applications of this framework I was just describing to both of these tasks. Now, again, just to kind of repeat this thing that Michael also went through, in general, we're going to talk about these message passing graph neural networks, which are by far the most common. And essentially, they just pass messages between nodes, and everything can be framed in these kind of two steps, where first you aggregate the message from your neighbors, and then you combine that message with your own representation, and you get a new representation. So that's everything that's been said already. And it turns out that this framework has a couple of problems, well, more than a couple. So for instance, it's a bit hard to encode higher order interactions in these sort of things, and that's more like a problem of graphs in general, not necessarily message passing. So, if you want to encode something like there's a high order interaction between 3 nodes, then because graphs just encode pairwise interactions, that's kind of difficult to do. You might be able to do that via features, but structurally, you can't essentially. Then you might also have these higher order structures. So for instance, rectangles. So maybe, for whatever reason, rectangles are very important for the problem you're trying to solve. But then graph neural networks don't explicitly kind of use these structures, right? It kind of has to search for it implicitly in some way. It needs to detect them. And we already saw in Michael's talk that even triangles, which are kind of the most basic structures, they can struggle with finding those. So, what about bigger structures? That's kind of a problem. Now, another thing is that you might have high order structures, so for features. So you might have some feature vector that lives on the edges of the graph. And then there's okay, how should we process these? Because, I guess doing in just classic signal processing on graphs, we just talk about some node features. How do we handle edge features? No one told us how to do that. Obviously, you can kind of do some reasonable guesses, but are those reasonable? What's kind of a principal way to process them? Now, there's also the expressive power problem. So you saw in Manka's talk again that graph neural networks are, or these message passing kind I've just described, are as powerful as this WL test. And there's a whole hierarchy. So you have also the 3 WL test that's more powerful than this one. And then you have a 4 WL and so on. And actually, if you want to, you can easily kind of increase the expressive power by just matching, kind of doing something that's equivalent to the next test. But then these tests are actually super computationally intensive. So actually, if you want to go beyond WL, you are kind of in trouble. And we don't really, this doesn't give us a framework to kind of trade off more easily expressivity and computational complexity. And again, we're going to see how topology can help us with that. And finally, we have long-range interactions. So again, because you do only these very local message passing, you need a lot of layers to make things that are very far away communicate, right? So if I have things that are like 10 steps away, I need 10 layers. That becomes harder to optimize, and deep graph neural networks also come with other problems we're going to see later. So preferably, you wanna find some way to make certain things communicate faster, potentially. Okay, so to solve these problems, where the kind of key observation is that all of them are, or to some degree at least, traceable to kind of the underlying space we work with, graphs, and the fact that they have a kind of simple topology or simple neighborhood structure, and we're going to see towards the end how that can be fixed more concretely from a topological perspective. But the idea is that Poincaré kind of comes to the rescue again, and in this paper in Analysis Citus, one of the main takeaways from that paper was that he was describing this kind of combinatorial way to look at manifolds. So essentially, you can split your manifolds in like these triangulations, so something we call a mesh today, and study these topological invariants are actually much nicer to study if you look in this kind of combinatorial perspective. And actually, algebraic topology, I don't know how many of you are aware of that, was called combinatorial topology for many years until, I don't know, I think 1930s or later, something like that. So yeah, and maybe that's perhaps a better name for the kind of things we're doing today, or at least in the first part of the talk. I guess there's going to be more algebra in the second part. Yeah, so essentially, to kind of fix these problems to some degree, we're going to notice that graphs are just one type of space in this hierarchy of this kind of combinatorial topological objects. So the next in the hierarchy are the simplicial complexes, which are essentially graphs to which we can also put some extra structure on top. So we can have these simplices, which are kind of higher dimensional objects. So if you look at the graph, it just has points, which are 0-dimensional, so the nodes, and it has edges, which are 1-dimensional. But then it stops there, but you don't have to do that. So you could put these triangles, which are 2-dimensional. You can have a tetrahedron, which again is 3-dimensional, and so on. And you can have, in this first kind of space, these are restricted to be simplices, so they kind of look like that, like kind of triangularly shaped, intuitively speaking. But in a cell complex, you do that, but you also are allowed to be more general, so you can have any sort of 2D surface. So you might have something that looks like this kind of a rectangular surface you see here. So you're not necessarily constrained to simplices, so you have a bit more flexibility. Okay, and the idea is how can we extend message passing on from graph neural networks to these type of objects? And to start with, I'm going to talk about simplicial complexes first, and we're going to follow sort of the same kind of historical story you've seen with graph neural networks, kind of going from convolutions and then gradually building up to message passing, and we're going to do exactly the same. So on simplicial networks, we're going to talk about convolutions, and on cell complexes, I'll talk about message passing. So the reason we do that is because it's easier to talk about convolution on simplicial complexes because they have a slightly simpler structure, and there's quite a lot of things to cover. So that's kind of the plan. Okay. So what's a simplicial complex? So you start with some vertex set, exactly like a graph. You just have a bunch of vertices. But then to kind of define more than just edges, you're going to have a collection of non-empty subsets of V called simplices. And these must respect some conditions. So first, you contain all the singleton subsets of V. So these will be the nodes, right? So if you just have a singleton subset, that's a node. But then you also have this restriction that this collection must be closed under taking subsets. So let's see some examples. It sounds a bit abstract, but it's actually quite simple. So first, a graph. Any graph is a simplicial complex. And here's kind of this collection and how it looks like. So as we said, we need to have all the singleton subsets. So we have 1, 2, 3, 4. These are our nodes. And typically, we draw these as simplices. So basically, if we have 1, 2, we just draw edge 1, 2, which is a 1 simplex. If we have 1, 3, we draw edge 1, 3, and so on. So it's very simple, just kind of a way to think about graphs, for instance, in this case. But as I said, we don't have to stop there. So instead of just having these singleton sets and sets of size 2, we can also have these sets of size 3. So we have 1, 2, 3 here. And this gives us this triangle, so these two simplex. So these are simplicial complexes. It's very simple. OK, now something that we do in algebraic topology, we kind of work with oriented simplicial complexes. So what does that mean? It means we can pick orientation for the simplices. So for instance, if we talk about edges, we have two orientations, right? Like we can go, what does that mean? You could think of this as a walk on your edge. So you can either go from 1 to 2 or from 2 to 1. So those are the two possibilities. And when we talk about oriented simplicial complexes, we denote them by these tuples, just to kind of specify the order. So before we just had a set, so that was unordered. Now we have these tuples where you have an ordering, essentially. Now, similarly, for instance, for triangles, you kind of have two ways to walk over this triangle. You can go either 1, 2, 3 or 1, 3, 2. And then they define two kinds of orientations. So you could think of this as kind of picking a reference frame sort of for your edge, but we're going to talk about that later. Yeah, so also just to mention again the notation for orientations. OK, so something to notice is that if we just ignore the starting point, we just have some equivalence classes. So essentially, if you just have an even permutation of your nodes, then you have one orientation that are all equivalent. And if you have an odd permutation, you have the other kind of orientation. So you have some equivalence. And actually, this holds in higher dimensional generalizations. We're not really going to look into that. But just so you know, even for higher dimensional things, you just have two orientations, kind of positive and negative. And that's pretty much it. OK, so then an oriented simplicial complex is simply a simplicial complex where we simply picked an orientation for each simplex. I should also mention that vertices have a trivial orientation, so you just have one orientation because they're just points, right? So it's kind of like a trivial thing. So we talk about orientations more when we talk about edges or triangles and things like that. Yeah, so that's just to illustrate that. And a classic way to pick an orientation for your complex, actually, a key result in algebraic topology is that kind of the topology of these spaces it's invariant with respect to the orientation you pick. So the orientation is more like some bookkeeping you are doing to do some interesting algebra we're going to see on these spaces, but it doesn't really matter what orientation you pick. But one common way to pick one is you can just order your vertices. So you just have V0 to some Vn. And then when you have an edge, so for instance, 0, 1, right? I just pick the orientation from the smaller thing to the bigger thing, right? I'm going from 0 to 1. If I have 1, 2, I'm going from 1 to 2, so and I pick that orientation. Similarly for triangles, if you see this kind of arrow, you go 0, 1, 2. So you always kind of walk in the order given by the vertices, essentially. So yeah, again, yeah.
The orientations on the simplex must be compatible in some way. In case on the 1, 2 edge, they must restrict to the same orientation, right?
No, not
also have the opposite.
Not necessarily. I guess for certain applications that's nice, but in general, for what we're going to do, like you can just pick an arbitrary one. But yeah, like for instance, when I guess in more geometric applications, you might want to kind of synchronize this so they're all kind of clockwise or something, and that's commonly done. But in general, you don't need to do that, and we don't need to do that for our applications today. Yeah, that's a good question. Okay, now it's getting a bit more abstract, so we can define on these simplicial complexes to do some algebra. We can define these vector spaces which have as a basis the oriented simplices in our complex. Now that just sounds kind of maybe a bit abstract, but it's actually very simple. So for instance, let me just give you an example. So we call these chains. So like if we talk about simplices of dimension 1, then we have 1 chains. If we talk about simplices of dimension 2, we have 2 chains and so on. So here's just an example of 1 chain. So you see these kind of edges that have been highlighted here, and we just took a linear combination of them. So we have 2.5 times this simplex 0, 1 minus 1, basically. I didn't specify the 1, but it's a minus 1 times 3, 4 plus 3.14, 1, 3. So very simple. Just you just kind of linearly combine, and you could think of this taking a real number of copies of that simplex, and you kind of add them together. And you can also do we can also have this convention that basically minus 3, 4 is same as 4, 3, right? Because if you have minus 3, 4, it's kind of moving in the reverse direction, so you have 4, 3. So there's just some algebra we can do. And again, for instance, we can also have 2 chains if we talk about two simplices. So again, here we just have 2 triangles. So everything will be just a linear combination of these, also taking orientation into account. So we can have something like 5 times the first triangle plus 4 the second triangle with the orientations you see in the picture, I think. Okay, now once we've done this kind of bookkeeping, what we can define is a boundary operator. So first, some notation. When we use this notation, you see here, we mean, so this is just a simplex, and we just drop the ith vertex. And when you do that, you get something on its boundary, so you can check that. So for instance, if you have an edge with just 2 vertices, if I drop a vertex, I get a vertex on the boundary of that edge, right? So it also works in higher dimension. Like if I have a triangle, I drop a vertex, I get an edge on the boundary. So that's what dropping a vertex gives you. And assuming we pick this kind of orientation given by the ordered vertices, we can define this boundary operator as follows. So this is, given what I've just said, this is at least partially intuitive. So you want to sum over everything on your boundary, right? So that's why it's called boundary operator. It gives you the boundary of something. So if you have a triangle, you want to sum over basically all the edges on that boundary, but to also kind of give you the right orientation, you have to be careful with the signs. So that's this -1 you see in front, that depends on kind of what vertex you eliminate. That just takes care of the orientations, and we're going to see in a second that just works basically. So we can do some very interesting algebraic operations like this just with surfaces, right? So intuitively speaking, it's something, you know, if you look at this, like everyone could say, okay, yeah, the boundary of that triangle or like field triangle, you know, is kind of those edges. And then if we take the boundary again, we just get nothing. So that's very intuitive, but it's actually very hard. And it took a long time, you know, in mathematics to get to the point where we actually can formalize these things. And this operator just gives us like a very nice way to do this algebra. And I find that quite fascinating. So for instance, if we just apply the definition to this triangle, we're just going to get v1, v2 minus v0, v2 plus v0, v1. So essentially, we get exactly those things with those orientations. So and that's expected, right? Because like we were going like that around the triangle, so we should also get these things to go the same kind of way, right? And now what we can do, like let's apply this boundary thing twice, right? So we just apply to the result from equation 1, and again, if you do the algebra and you look at the signs, you'll see that things cancel and you get 0, right? So this is just very magical that, you know, we can do this algebra that describes the surface, and I find that pretty cool. Okay, so you might ask, you know, is the last result of coincidence? Like we applied the boundary twice and we got 0. Does that happen in general? And the answer is yes. So there's everything relies on these results. So the boundary of a boundary is 0. So that's very intuitive, right? Like if you have like some closed compact surface, you take its boundary and then you think, okay, that doesn't have a boundary anymore. It's kind of like a loopy thing, right? So that's just formalizing this thing. So essentially, that means if we compose these boundary operators, we just get 0. And that's another way to think. So these operators are linear. I should have mentioned that. And another way to think about this is that the image of the first operator is in the kernel of the second operator. So yeah, everything that's kind of in the output of the first operator must be sent by the second operator to 0. That's just the way to say it. Okay. And here's like the proof is super easy. So essentially what you do, again, apply the definition for the first boundary operator and then apply the second operator. And now notice that we can kind of split this in two, right? So first we need to remove one vertex from what's before VI and another vertex for what's after. So for what's before, it's just the usual definition you would expect. But for what's after, because this thing has disappeared in the meantime, we need to shift the index of this -1 by a 1, right? So we see that we have in the first sum, we have -1 to the power j plus I, whereas here we have j plus I minus 1. So, and their parity is different. So one will be a minus and one will be a plus. They cancel and this is 0. So that's the intuition. Okay, and we can use this to do, again, like very simple intuitive things that are very hard to formalize. So for instance, let's try to formalize what a hole is. So I've just plotted here 2 one chains, and the difference is that kind of one specifies a hole, like on the right, but the other one is not what you would call a hole, right? Because it has some stuff inside. So let's just formalize in terms of these boundary operators what we mean by a hole. How would you define that? So first, let's see what they have in common, right? So what they have in common is that they are both cycles, which means they don't have a boundary, right? So when we take the boundary, they should be sent to 0, right? Because they're like a loop, they don't have a boundary. So they both have that in common. Now let's see what's different between these two examples. So what's different is that the first chain is also in the image of the kind of higher order boundary operator. So what does that mean? It means it's on the boundary of something itself, right? So this orange thing is on the boundary of what's inside. So that gives us a very nice way to define what holes are. So there are these cycles that are not on the boundary of something else. And this is called the Kth Homology Group, and it actually works in higher dimensions as well, kind of magically. So it's just a quotient vector space or quotient of groups, depending how you want to look at it. But essentially, you just have what I've just said. So basically, all cycles that essentially are not, and we get rid of things that are on the boundary of something else. And that's kind of just the math way to put this intuition into words. And again, like very intuitive things that we can do with algebra. Okay, so just want to say that these boundary operators, they are linear. We can represent them as a matrix. And it's very easy, like essentially, so the first boundary matrix is just the incidence matrix of a graph, but it's signed. So each source node shows up with a -1, and each target node shows up with a +1. So where source and target depends on what orientation you picked, essentially. And again, for the higher order boundary operators, we have triangles for the columns and edges for the rows. And again, you just pick like a -1 depending on how you picked your orientations, or a +1. So that's very simple. So now we arrived we're approaching kind of convolutions on these spaces. So we can define what's called the Kth Hodge Laplacian. And this has been studied by, you see here, quite a lot of papers. So if you want to look in more detail, I've just put them here. But essentially, you can factorize this Laplacian. So actually, first, what it was a linear operator that can operate on these k-chains. So you give it a k-chain, it gives you another k-chain. So that's all it's doing. And you can decompose it into this lower Laplacian and an upper Laplacian. And the lower is just this composition of boundary matrices. And the upper is this other composition of the next kind of boundary matrices. So this kind of goes through sort of specify things that, actually, I just say this on the next thing. So essentially, first, let's use some notation, actually. So, OK, if we have two simplices, we use this notation if they share a k-1 simplex. So essentially, they're kind of adjacent because they have a common thing on their boundary. Well, that's what that means. So for instance, two nodes that have a common point, that sort of thing, or two triangles having a common edge. And we could also have like sort of an opposite of that. So we have two things that are on the boundary of the same k+1 simplex, and then we say they are upper adjacent. So that's the notation. And what these Laplacians, they're called lower because because it encodes lower adjacencies. So you're going to have some things on the diagonal, some numbers that depend on the dimension you work with, and then you're going to have a plus or minus one depending on the orientations. It doesn't really matter right now, but yeah, idea is like whenever you have lower adjacent things, you have a plus minus one, otherwise a zero. And similarly for the upper one, you're going to have this what's called an upper degree. So how many things that are upper adjacent to it. But again, you have a on the diagonal. But for the other terms, you just have plus minus one if they're upper adjacent. And again, the sign will depend on the orientation you pick. And importantly, you should see these as a generalization of graph Laplacian. So the graph Laplacian is just the Hodge Laplacian in dimension 0, so for nodes. And it's defined just like this because the other term disappears because it's just 0. So you just have these B1s. That's because like you have a B0 that's 0. So it just disappears. And you can show this is equal to the degree matrix minus the adjacency matrix, which is kind of the classic graph Laplacian definition you see. All right. Now, let's plot some eigenvectors of this Laplacian just to kind of get a qualitative feeling for what it's actually doing. And surprise, surprise, we see that the energy of this vector, so this is the eigenvector with eigenvalue 0. We call these harmonic eigenvectors. You see it's very concentrated around the hole, so you know what's going on. And there is this result, it's called the Hodge theorem, that the kernel of this Laplacian and the homology group we just defined are isomorphic vector spaces. So you can sort of identify for these holes some eigenvectors with some eigenvectors of this Laplacian. And something very interesting is that if you look at the rank of your sorry, yeah, actually, I should have said that this should be the dimension of the kernel, actually. That's a mistake. So yeah, you can check that the dimension of the kernel of this Laplacian actually equals the dimension of this vector space, obviously, because of the isomorphism. So that means you're going to have one eigenvector per hole in your surface. So this is kind of like a topological property. Even if we deform this mesh you see here, or simplicial complex, and we kind of homomorphically speaking, and maybe we add more triangles and whatever, that's not going to change. We're still going to have a kernel of dimension 1. Okay, so let's arrive at the first convolutional network. So first, we'll normalize this Laplacian, and we'll just use a very, very simple normalization. So we just put a constant alpha in front of the Laplacian, and we can make this alpha as small as we want, and that just compresses our spectrum and does the normalization. And we're going to have some features for the k simplices. So this will just be these k chains, but we can have kind of multiple feature channels, so d feature channels. Okay. Oops. Okay, so first we can build some sort of graph convolutional network. Actually, you can show that the graph convolutional network, here you might have seen like the kind of normalized adjacency matrix, But when this delta 0 is the normalized graph Laplacian, you can actually write that as identity minus delta 0. And here we sort of generalize this. We have a different kind of delta 0 because we do the normalization slightly differently. But you could think of this as some sort of GCN, right? And you have some features. You put like a matrix, and then you pass that through some nonlinearity. So the simple sort of convolution you can think of. Now, here's some interesting result that you can prove. So by just applying some standard results from, so there's this proof technique from this paper by Ka and Wang. Essentially, you can show that if you define the Dirichlet energy of a signal, so that's just this operator, which essentially, we're going to look in more detail, I think, later. But essentially what that tells you is how harmonic my signal is. So it's just an energy. Like the closer it is to 0, the more harmonic, or the closer that signal is to the kernel. So what you can show is that with this convolution, the energy at the next layer is upper bounded by the energy at the previous layer times some factors that depend on the spectrum and the norm of these matrices. So essentially, if we make alpha super low, these lambda star will also become low, and you can show that this model converges exponentially to the kernel. So what's the implication of that? So the main idea is that deep linear graph convolutional network and simplician versions are topological in behavior in their asymptotic limit. So again, we see some sort of result that's kind of we found in some sense like a topological invariant. So like even if we change our underlying space, or like if we deform it, in some sense we will always converge to this subspace that has a dimension given by this kind of number of holes, right? So in some sense the kind of long-term behavior of our model is topological. And this was actually known for GCNs, and actually doesn't hold just for linear. So for GCNs, you can prove, and this is the paper by Kai and Wang I was mentioning, and there's another one I'll also mention later by Ono and Suzuki. That was iClear Spotlight a few years ago. But essentially for GCNs, you can generalize this to ReLU activations as well. So even if you put nonlinearities, you still get the same behavior. And what does that mean? Essentially, you're going to converge to like a signal that depends on two things. So the connected component, because the Kth Homology Group describes connected components. It's kind of the holes in that dimension. And the degree. So here, because these two things have the same degree, and they're in the same connected component, they're all going to have the same features. That's why I colored them the same. And let's say your graph has another connected component. Again, they all have the same degree, and they will have the same feature in the end. So you get this topological behavior or like convergence of the features. Now, if you have like the general case we were just discussing, the features converge to a signal whose energy is concentrated around the hole. So and this also works in higher dimensions. So like in whatever dimension you're in, although here I need to specify that this holds only for the linear case by the result we just seen before. So that doesn't really work because of some complications with orientations. You can't consider ReLUs. So yeah, I think it's fascinating that these models are kind of topological in behavior without us building them to be, and that's quite common in geometric deep learning, or like in models operating on some space. It sort of inherits some of the properties of that space, or it's limited by those properties to some degree. And yeah, this is what I've just said, because this BK is a topological invariant. The dimension of the subspace we converge to is kind of a topological invariant. Okay, now here's another result in Hodge theory. So it's easier to visualize this in like a continuous setting rather than on this kind of simplicial complexes. So I just put like the continuous version. But essentially, if you have like some sort of vector field on your manifold, informally speaking, it's a bit more complicated. But if you have something like that, you can decompose it in like kind of a rotational component. So you have these curls, and then you can have as your second component the harmonic part. So this kind of depends on the hole. So you can see it's like a very, it's kind of the smoothest thing you can get on that surface. And then you have something that looks like a gradient. So you can decompose any signal into these kind of subspaces. And this diagram is inspired by a similar diagram from Keane and Crane. Okay, and I'm going to explain why I mentioned this in a second. So we have like kind of a zoo in recent years, similar with like geometric deep learning. We have a zoo of simplicial convolutional networks that emerged in past years. And in our paper, which was one of the first on this topic, we show all of these, and even the future ones that show up later can similarly be expressed as some sort of message passing, and we're going to see that a bit later, how that message passing looks like. But in general, like we can work with some convolutional, relatively general convolutional model. So they all these convolutions kind of look sort of like this. So okay, let's go through this. It's a bit long, but it's actually quite simple, right? So you have something like the lower Laplacian, but here you could also have anything that has the sparsity of your lower Laplacian. So or encodes those type of adjacencies. So you could put an attention matrix here or something like that, and that was done in some works, including one of ours. But yeah, the point is you have a lower Laplacian. Again, put like your features, use some weight matrix. Again, you have upper Laplacian. Then you can also move signals from the level below by using boundary operator transpose. So this is you move vertex signals to edge signals. That's what this does, and then put it in your transformation. And then you can do the other way around. You can go for these rotational components I was mentioning, you go from triangles to your edges again, and you can also just have something that processes your features. And pretty much all the convolutions that were defined, I think actually all of them look like this up to some change in these kind of diffusion operators. So we're just going to use this as a model to prove some interesting things. Okay, and yeah, you can also motivate this factorization through kind of the Hodge decomposition you've seen, because you essentially some of these things kind of give you like the non-linear version of the rotational components and all these things. So that's another reason to see why maybe it's a good idea to decompose things like that. Okay, so let's talk about symmetries, and I guess this is more like the geometric deep learning part of the talk. So essentially, we can also define some symmetries on these things. And again, it's the permutation group first. So we have permutation equivariance or invariance, depending on what exactly we're doing. But yeah, like essentially you can define I should specify here, you could have two options. You can either permute your vertices, and that induces some permutations on the higher order things. Or you could treat all simplices of different dimensions as sort of independent and kind of permute them independently. So we take the second approach just because I feel it's easier. So basically what you do, you just have some permutation matrices with the right sizes. So this is a matrix to permute the nodes. Then you have one to permute the edges and so on up to dimension d, whatever. So whatever your highest order simplex is. And then we can specify the structure of the complex by just the boundary matrices. So just put all the boundary matrices in a list. And then we can just permute these things. So for the first boundary, you need to permute the columns by the kind of the edge permutation and the rows by the node permutation and so on. So then if we just have some function between these chains, we say it's permutation equivariant. If we just, you see the classic equation, I think you're tired of it already, how many times you've seen this. But essentially, you can permute first all these boundaries and your features, and that's the same as kind of just permuting your outputs for the kind of untouched features. And we can just see, for instance, I've just picked like a simple version of the convolution you've just seen, just to kind of not have too many things in there. But anything of this kind is permutation equivariant. And it's very easy to just show this by just doing the linear algebra. So actually, if you just do these matrix multiplications, you're going to end up with this matrix in the beginning. Anyway, it's very simple. So yeah. Okay. But there's also an extra symmetry that emerges, and that's quite interesting. So we talked about these orientations, but the thing is, you don't want your outputs to kind of be messed up completely if you change your orientation, because we said the orientation is kind of arbitrary. It doesn't really matter which one you use, it's just for bookkeeping. So let's just look at an example for a case where we have kind of no message passing, we just have one edge, right? So what does this mean? Like, okay, we go from V1 to V2, we have this orientation. So this number 3, you could think of it like, a feature living on that edge. You could think of it like the velocity of a vehicle moving from V1 to V2, right? So let's swap the orientation of this thing. Then we go from V2 to V1, but we still go with the same velocity in that direction. So that means we need to change the sign here, right? It's like saying, okay, I'm going with velocity -3 from V2 to V1, right? Which is the same thing. I'm still going that way. It's more like a frame of reference, right? That's what this says. But what we could do is like, okay, we want to apply some convolutions or functions on these things, right? So first apply a function on this feature, you get f of 3. And now let's say we switch the orientation now, we get minus f of 3. But if we went the other direction, we would have f of minus 3. And obviously we want this to commute, so these things must be equal. And the corollary from this thing is that our function must be an odd function. So it's just, f of minus x must be minus f of x. And this is kind of a requirement for these convolutions. So how exactly do we kind of talk about orientation equivariance? So what does it mean to flip your orientation? So essentially, if you flip your orientation, that means you change your orientation with respect to everything that's connected to you. So in this diagram, what I did in the second row, I switched the orientation of this edge you see highlighted in red and also of this triangle. So that means this column where these edges show up, it just kind of reversed all the signs. Also the row where it shows up in the kind of other boundary matrix. And similarly for the triangle, you just multiply by -1 that column, and that just flips everything. And notice that the sort of relative orientation between this edge and this triangle didn't change because you multiply twice by -1, so it didn't change anything. So that's because you changed the orientation together. So we sort of want to be equivariant to these sort of changes in our matrices, which is kind of like a change, it's essentially a change of basis, but it's like very simple changes you can do in this vector space. Okay, so that's just kind of defining orientation equivariance based on these things. How am I doing with time? Because I'm not sure when we started.
Well, we started very late, so I would say up to 50.
Okay, yeah, that should be good. Okay. All right, so yeah, so now we can just define some matrices, T0 up to TD. And these matrices are just diagonal matrices, and their values are ±1. So they're just some matrices to perform these sign flips, right? All these do is like they flip the signs of columns and edges depending on how you multiply. Also, we have to put some restrictions. So if for T0, the one for the vertices, it must be the identity because we just discussed like vertices don't have or they have a canonical fixed orientation. They don't have multiple, so we can't flip the orientation of a vertex. So that must be the identity. But for the others, they could be whatever that respects the structure. And then again, we can just kind of express this kind of transformation by just multiplying each boundary matrix by the right matrix, by the correct matrix from the left and the right. So yeah, this would be identity all the time, for instance, but T1 essentially flips the sign of the columns of B1 and so on. And again, we can define orientation equivariant as before. We just replaced the kind of the permutation matrices by these kind of sign flipping matrices. And we can just prove that when these nonlinearity is odd, which is what we were already noticed, but it turns out that's kind of sufficient for these convolutions, you get orientation equivariance. And to see why that happens, like just on some minimal example, again, you can kind of do all this linear algebra, and you end up with something like nonlinearity, and then the first matrix you have inside is this sign flipping. So we want this nonlinearity to commute with this kind of sign flip matrix. And that happens exactly when this psi is odd. So just because we want to move this T1 outside, because you see here we have T1, this Tk is outside the function. So if we swap these two, we just get F here. So that's just a simple proof sketch for these types of convolution. And this sort of result can be generalized to message passing. So for message passing, we have some results in our paper that you see here at ICML. And we kind of show how you can generalize this. You still need odd functions, but you also need to be more careful with like the message functions and so on. So in the more general setting. Okay, now let me talk about these things that are called chain complexes. So these are just a very fancy way of saying that we have all these vector spaces we talked about, the K chains, but we can put them in a chain, right? And essentially, these elements are related by these boundary operators. So at some point, you're just going to have 0 because you don't have anything beyond some dimension. We always assume some finite dimension here. And then, you just apply boundary operator and you kind of you move to the right, essentially. And what I want to mention is that these convolutions are essentially convolutions on chain complexes. And actually what these boundary matrices are doing that I highlighted here in red, they move information up and down this chain, right? Because the boundary just kind of moves things moves features from the kind of vector space above you and the one below you. So that's what's going on. So essentially we can see these as convolutions on these chains. Now, there's a very interesting consequence from this perspective. So essentially because of what you have with like that the boundary of a boundary is 0, unless you put a nonlinearity there, you can't have things that are 2 dimensions apart communicate. So you can't have, okay, I don't have but yeah, basically you can't make C0 communicate with C2, which would be somewhere here, right? You would only have these kind of very local communications, and let me show you exactly in a proof. So if you look here, so assume that psi is the identity, and let's see what happens. So if we just see how information from 2 chains propagates to 0 chains, so the vertices, you just get an expression like this, where you have B1 times B2, right? Because like to get from triangles to like vertices, you need to first go through B2 and then B1, right? Boundary and then another boundary. And then you'll just get a 0 there, and this is 0. So if you just stay with like linear transformations, actually you can't make things that are very far apart communicate, or not even far, not very far, right? Or like even very close, I would say, right? 2 dimensions apart. So this kind of shows why nonlinearities and might be like a very important aspect, or kind of you have some additional expressive power in some sense if you use nonlinearities. Okay, and so here's kind of an application for this thing. And what I forgot to mention when I was talking about this kind of topological characterization of the kind of infinite layer behavior of these models that we were seeing before, where you converge for GCNs, you converge to connected component dependent signals, and for edges you converge to this kind of homological high order homology features, is that connected components are super boring, so they don't really help you with anything in general, or like it's so smooth, like if you just have a constant signal for a connected component, it's unlikely it's useful for any classification problem or anything you don't grasp. But actually, if you just work at the edge level, it's interesting that these extremely smooth features, you converge to these topological features, they're actually much more interesting now, right? Because like cycles might be super important for certain problems. So now this kind of can give you some sort of way to localize cycles in space and potentially learn some very complicated features that are a function of things living around that cycle. So you already get much more complicated behavior in higher dimensions with these high order homology groups. And we're going to see in the next talk how we can get even more complicated behavior by just staying at the vertex level by putting some extra structure. So just kind of a teaser for the next part. Anyways, so what we do here is we want to classify flows on these type of spaces, and we represent flows as one chains. So basically, just imagine these are some random walks. Actually, in the first case, they are random walks. So essentially, if you walk through a vertex to another one, you just have a +1 if that agrees with the orientation, or a -1 the other way around. So orientations help you kind of specify the direction of your walk, essentially. And we just model that as a chain. So like just a linear combination of all these things, or as you saw, like just taking these kind of coefficients in front and adding up everything together. And what we want to do is classify the red trajectory and the blue trajectories. So we're going to have some blue trajectories that are all going sort of like this, but they're random. But they go around this hole at the top. And we have some other trajectories that go around the hole at the bottom. And another similar example is here, this is some real data set of ocean drifter trajectories around Madagascar. And they kind of give you like a sense of the kind of ocean flows or currents or things like that. And what we're doing here, we're classifying flows that are clockwise versus anti-clockwise around the island. So I think clockwise are mostly these ones you see clustered in the bottom right, and the other ones are kind of clustered there. If you actually visualize them, you'll see that those are kind of the 2 clusters, roughly speaking. And again, like because this has to do with orientations, it's actually super helpful to have is orientation equivariance and all these things and all these kind of convolutions you saw on these one chains. So here are some results. So here we just apply some GNN and we made it invariant to these kind of orientations. So we just apply a GNN on the line graph. So essentially, whenever we had like two edges connected by a vertex, we were just transform that to like two nodes connected by an edge, right? So that's just kind of a dual perspective, just to model it as a graph for the GNN. And you can see in general it was struggling even on like kind of training data set. Then, for instance, if you consider something like with ReLU activations, so the MPSN is message passing Simplicial network, so that's our model. It can do very well on the training data set, but what we did on the test data set, we randomly flipped the orientations just to kind of see how these models kind of are doing. And you see when we pick like a nonlinearity that's not odd, the performance just collapses to random on the test data set because the model was massively confused by the change in orientation and it got like some very different outputs. But when you choose like some odd activation functions like the identity or the hyperbolic tangent, you can see the model learns to generalize, and it's also these kind of simplicial models are also doing much better than GNNs on kind of these sort of tasks. And we're going to see, I guess, more kind of practical applications in the second part, which I'm moving to now. So far, we just to take a break and kind of yeah, maybe also questions if there are any questions for this part. Yes. Okay. No, it's fine. What was the slide about? Yeah.
So the right picture says due to converter signal, percentage concentrate around.
Yeah.
So actually, I think the question is a bit like twofold. In this case, it looks like we're actually highlighting one chain over two. It's like either an edge, or not.
Yeah.
I believe you're doing like Laplacian, so you have to do like.
Yeah. Yeah, so
I believe that when it can convert to something to a graph, but you would need at least a little bit of noise or up edge around that chain, because that specific one is the one that
yeah, so I guess just to repeat the question, if I understand correctly, basically you're saying it's not going to converge to something looking exactly like that.
It can sort of convert to something that's quite close to one chain, but quite to one chain because it has two chains here, right? So it needs wraparound triangles, not U.
Yeah, exactly. So actually, yeah, so I guess I was lying here a little bit that you might get something, you generally get something that looks a bit more messy, so it doesn't look that nice as you see here. But in general, if you actually plot this and you look at the kernel, you're actually going to get something that looks, okay, maybe it's too much to go back, but like you saw that there, and actually often when you plot these things, they're very nicely concentrated. Yeah. Yeah, I think. Yes. Yeah, so actually there's a paper where they use these sort of convolutions to find optimal generators like this one. Yeah, it's the one by Vidit. Yeah, so there, and I guess like that's one of the things you get from these convolutional models, that you might not get like a perfectly nice thing around the hole, like that's exactly like this, but you probably get something more messy. Generally, when you plot this, they are pretty well concentrated, I would say. But then you also have the kind of learning bit that kind of learns to take into account all these things and kind of piece the things together. So yeah, it might look more messy. Yeah. So, okay, yeah. Okay, yeah. Yeah, we can chat now. Yeah, other questions? Yeah, maybe.
Can I ask I think it's just like 1 or 2 slides off, but where you give the general form for convolutions. Yeah, so you say this is like the general form where you've got like total freedom in all the distribution definitions, but is there like special cases where you would impose restrictions on what they are? Like what sort of, if that's the most general form, are there like significant applications in which you would pick something more specialized?
So here, just okay, the question is if like, if this is the most general form, I guess like is it sufficient for kind of most applications, or you need something more complicated and where you would use that, right? I think that'd be.
Yeah, or if you like using the interpretation you gave before, like there's the curl mix and the divergence bit, would you like specialize to only use like one of those ones?
Yeah, I see. Okay, so yeah, so I think here maybe just to clarify, I think the battery is running out here for this thing. Essentially, it's not the most general form. I would say it's more like this was general enough to describe all these methods I've seen so far, but I would guess like this will cover mostly everything. Like if you look at graph convolutions, they all have like some sort of diffusion operator as well, because of some sort of Laplacian adjacency, whatever, feature, weight, and maybe you could have some residual version of that. In general, like that kind of covers lots of cases. Obviously, when you do message passing, you do something much more general, and I'm actually going to talk about that later, where having that extra generality might help with certain bits. Yeah, so maybe, yeah, you can ask again if that's not answered later. Okay, I think Lorenzo had a question.
What's your opinion about representing simplicial complexes as graphs, as line-of-type graphs? So, in general, how much information do you use, in your opinion, using graphical networks for handling this type of problems?
Yeah, so I guess to some degree that's more like a conceptual thing. Each of these terms here is a graph, right? Like you just have some adjacency that has some entries. So we just decompose these things in like a series of some sort of graphs. I guess these boundary things are a bit like of an exception because it's not like a, like a regular adjacency matrix you see. But often I see in papers like, okay, yeah, we kind of did something that's more suitable for GNNs, but I don't think it's really new. Like it's just the way you look at things rather than so much of an implementation issue, I guess, or a difference. I guess it's mostly, I guess, the differences in implementations will show up at these boundaries. I think probably, if you have to do something with orientations or you want to exploit like topological structure, and you think that's useful, probably kind of being aware of these orientations and taking them into account helps. For other cases, it might not. And actually, in the second part, we're not using orientations, and that we still have some benefits from that, and maybe that will be answered there. Okay. Other questions? Okay. How am I doing with time again? 15 minutes now, or is it?
19.
Okay. Sounds good. Thanks. Okay, let's go back to where we were. Okay, so now we just generalized these to message passing. So in our previous paper, we also defined these on simplicial complexes, and then we generalized this to cell complexes, which also covers the previous case. So we can just look at this case straight away. So now cell complexes, why do we care about these? Well, we just saw that these simplicial complexes have this subset inclusion property. You always have to have these simplices, and then that can be kind of restrictive. But at the same time, you can, we want to maintain some of that theory, but, kind of have more flexibility at the same time. So that's offered by the cell complexes, which essentially, this is like a semi-formal definition if you want, but essentially what they are kind of like, again, we can have these two-dimensional or higher dimensional things, but we obtain them by sort of gluing things of various dimensions together. So, for instance, you would have things that are, the only restriction now is that these pieces of the puzzle, they must be homeomorphic with a disk of the respective dimension, right? So if you have like what's called a two-cell, now we don't require it to be like a, like a triangle. Only thing we require is this to be homeomorphic to like some disk, basically. So now it can look like this, right? And we also require these gluings between these things to be nice. So you could do some very weird gluings here and end up with some very weird surfaces. We don't look at that. We just have these kind of nice puzzles where you kind of attach these things nicely together. That's the whole intuition. I don't think you need to look really over the formal one. Now, something you might wonder, okay, like, and this is actually something you could wonder also for simplicial complexes, and maybe you could have asked this, but you know how, or maybe you wondered, how do we get these things, right? Like, I guess in the previous example, for edges, that show up naturally, but in general, everyone gives us a graph data set because that's what we have. No one's going to build for you a cell complex data set. So where do you get those to kind of actually apply these things? And the kind of answer is that these cell complexes are actually traditionally built in a hierarchical manner and sometimes even defined like that. So essentially, you just start with, like, let's say a graph in this case. And what you do, for instance, you can find some cycles in this graph and glue the boundary of these disk to these kind of structures. So you would have to kind of decide beforehand what are the important structures in my data set. So if cycles are important for you, then you can glue these disks to any cycles, and then you get like a two-dimensional cell complex. So that's kind of essentially you identify some substructure to which you can glue these disks, and then you use that. Okay, now you already seen the Weisfire elementars, but maybe it's useful to go again through this, and you can at this time you can also see why these two things are found to be equivalent by the Weisfire element test. But essentially, you start again with two graphs that have the same colors for all the nodes, and you keep refining these colors as you saw before. So you'll see that at the first iteration, so you just injectively map these neighborhoods and the color you're hashing at to like some new color, and this operation should be injective. So it's like perfect hashing or something of that kind. So at the next iteration, you get something like this. If you apply this again, you get the same sort of color distribution. Obviously, your colors change because your inputs changed, but like the same nodes will be colored the same like at the previous iteration. So that means you converge essentially, and then you stop. You can look at the histograms you have for the nodes, and if these histograms are the same, then the test is inconclusive. And we can see here these two graphs are non-isomorphic, as you already seen also in the previous talk, but these histograms are the same, so the test failed to distinguish these. So also a corollary from these, WL can't distinguish triangles, right? So the second graph has triangles, the first one doesn't. So we can infer from this it can't distinguish these things. Also, you can say the same thing about squares, which is kind of intuitive, since I guess they're more complicated than triangles in some sense. Okay, so what we do in this paper, we generalize this test to cell complexes. And so far, we kind of seen with this kind of Hodge theory type of results, how results from topology kind of have implications for our models in graph theory, but we can also do kind of the other way around, take some very practical ideas from graph theory and apply them to topology. And so now we kind of see the reverse direction and see how these two fields can inform each other. So what we are doing here, I'm just showing one iteration because it's a bit more complicated and we have more elements and it gets messy to show more. But essentially here also, you also start here with kind of the same color for everything, but I've just colored everything with a unique color so you can see how this hashing works. So this is more like just for educational purposes, I guess. But yeah, like what you do is, so first as before, we were hashing the color of the node we were refining the color for, right? So now we are talking about this yellow edge. So we have like that color, that's the first thing we hash. Then we hash the colors of the things on the boundary, so we have two vertices. Then the co-boundary, which is just this higher dimensional thing, the yellow thing is on the boundary of, so this triangle, we put its color there. Then we have upper adjacencies, which are kind of given by these Laplacians, these upper Laplacians that we talked about. So essentially this yellow edge is upper adjacent to this edge and this edge because they're all part of the same triangle. Right? Then we have lower adjacencies. And again, if these are also lower adjacent, but then you'll have an extra thing that gives you a lower adjacency, this yellow, this orange edge, because they share these vertex here. So that's what lower adjacent means. They have a common thing on their boundary. And we include basically those edges, but we also include the kind of the cell that connects them. So in this case, for instance, we also include this blue node from here, not just the orange color of this thing. So we basically include everything just not to miss anything. And we see that there's some redundancy in that in a second. Okay, now once we do this, we can show that we gain something. So essentially, we call these things lifting maps. So like how I was describing how we can attach these two cells to like some cycles, we call that the lifting because essentially you lift your complex into something higher dimensional. But there are multiple ways to lift, right? So for instance, one is to attach to all cycles, a two cell. One is to induced cycles. And what I have, I think it was, oh, actually this was cliques. Yeah. So actually, yeah, so you can attach these to cliques. Basically, you can attach to induced cycles and cycles. Okay, so you can have you have at least these three strategies to build a cell complex from a graph. But the idea is like, if you apply one of these lifting strategies, and so you take these two graphs, you attach these cells like we specify here. So for instance, for cycles, you'll put a two cell here, another one, oops, another one here, and so on. Then you apply this color refinement I've just described, you can actually distinguish more things, and that's quite easy to see here because, for instance, once you kind of explicitly model these cycles, the test can very easily figure out this thing has a 6 cycle, this one has a 5 cycle, and the color refinement will easily figure it out. So you have like a very explicit way to model these higher order things and distinguish graphs more easily. Okay. But there's also a problem with these kind of adjacencies I've just described. So what might happen is that you'll start with like a very sparse graph like this. So the star graph is as sparse as it can get, roughly speaking. But if you think of in terms of lower adjacencies between these edges, everything's connected to everything, right? Every edge here is lower adjacent to every other edge. So your like computational complexity explodes, right? You might have, imagine you have a star graph with 1 million nodes. Like a graph neural network would like, just that'd be super easy for it. But here you'll have 1 million squared computations because of this thing, and that becomes a problem. So then that kind of forced us to look at this and prove this result that essentially you can, at least from this kind of WL perspective, you can get rid of some of these adjacencies, and in particular the co-boundary adjacency and these lower adjacencies. You can get rid of them, and your expressive power is still the same. So you'll still be able to distinguish the same cell complexes, even though you get rid of these things. And that has like useful consequences for computational complexity. And actually, before we trained these adjacencies, we couldn't get the model to even fit in memory. So we had some very big problems with that. Anyways, so let's just define this message passing. And we will just use, as a consequence of this theorem, we'll just use those types of adjacencies that are left. So basically, that means you'll have some boundary adjacencies and some upper adjacencies. And it's very similar to what we do on GNNs. You have some messages, but you have two types of messages. So one, you have the boundary messages, which are these orange lines here. So you can see vertex communicates with the edge that it's on the boundary of. This edge communicates with the two cell, that's because it's on the boundary of it. So you'll have these orange boundary adjacencies, and you pass messages and you do aggregation. So you'll aggregate, for this edge, you're gonna aggregate these two messages using some nonlinearity or whatever, but something of that kind. So we literally just generalize what we do on GNNs. With upper adjacencies, these are the blue lines. So at the vertex level, upper adjacencies are just the usual graph adjacencies. So at this layer, it's sort of, you kind of behave like a GNN to some degree, right? Because you have the same adjacencies, but then you also have upper adjacencies at a higher layer. So for instance, here, all the edges part of this cycle, or on the boundary of these two cells, they're upper adjacent because they're part of these two cells. So they all communicate with each other here. So you kind of have like quadratic messages here inside. Everyone communicates with everyone in this loop. So that's what these blue lines show. And then, as before, you just have an update function that takes as input these messages. So you have the boundary message, the upper message, and the kind of old features at that cell, and you update it and you get the new features at the new iteration. So that's everything that's going on. And then at the end, we just use the readout function. So basically, if you want to get a single vector for the whole cell complex, essentially what you can do is, well, you need to aggregate all your vertex features, edge features, two cell features in a permutation invariant manner. And we kind of put like these in separate entries because they have separate dimensions. So for instance, you could use different weights for these things because you can distinguish them. And I should say that these types of message passing have also been kind of explored concurrently in some other papers that you see here. Another thing to note is that compared to GNNs, this gives us like a hierarchical message passing. So we can encode to some degree these things that Michael was talking about, where you kind of zoom out and you have this kind of hierarchical perspective of the world. With graphs potentially like in kind of the raw form, it's harder to include that. But here we kind of get this naturally. Okay, and in terms of expressive power, we can just use kind of some sort of classic results to show that when you kind of design your neural network in certain ways, so if your like kind of class of functions is expressive enough, you can be as powerful as this kind of cellular WL test. So essentially you can do whatever that test is doing. And to kind of test that, here's an example where we were testing distinguishing strongly irregular graphs. So these are some very symmetric graphs. Actually, I should have included a plot here, but there's like very, very regular and symmetric looking graphs. And GNNs really struggle. So our model is in orange, and we plot here the failure rate. So lower is better, essentially. And the blue is just kind of one of these GNNs. As a red line, you see 3WL, which is already more powerful than WL. And you can see that 3WL, which has like a pretty bad computational complexity, it completely fails to distinguish this. And this is a theorem. It can't distinguish strongly irregular graphs. But actually, when we kind of do our message passing, which has relatively good computational complexity, or certainly much better than 3WL in certain settings, we can quite easily distinguish most of these graphs. And kind of a requirement for that is to consider cycles that are big enough. So the bigger the cycles you consider, the more freedom you have. Okay, another thing you get from these are long-range interactions. So I was talking about this in the beginning. Essentially, with GNNs, you need to kind of do this, very boring hopping from one node to another. And if you want to get from the green one to the red one, you get bored there. But here, like you just jump into the two cells, or the two cell kind of creates a shortcut for you, and then you jump back to the red node, and you can do that in the constant number of steps. So even if this cycle has like size 100, if you model it as a two cell, you very easily jump from there to there in a constant number of layers. So you don't need to use more layers just to make things far apart communicate. And this is important for molecular applications where often atoms on opposite sides of a ring, they might have important kind of information for predicting various molecular properties. So I want to kind of give you the topology, maybe the slightly more, point set topology perspective of this. And the consequence of these long-range interactions that are now allowed is that we sort of implicitly can consider another topology on our space. So before, let's define. So there are these star operators, which essentially give you like an open set around a point. So like for instance, that star essentially considers all the cells having your cell as a face. So in the graph case, well, there's just the node where you are, and also the edge is incident to it. So that's your open star. And also for the red node, and you can see these things don't communicate. Essentially, the combinatorial structure of the graph is a result of these open cells and how they open sets and how they overlap. But now in the cell complex, if we kind of plot the star operator, we have these neighborhoods, and actually these stars induce a topology on this space, and we're going to see that in the next talk. We use that. But now, like these are much bigger, so you can see how these neighborhoods are kind of reaching out to a lot of other things in here, and you can see how the green bit and the red bit, which now shows the open stars for the green and the red node, now they overlap. So that's why we can kind of communicate much faster, right? So what's the idea here is that relational information essentially comes from the topological structure of the space, right? So instead of thinking about graphs as just these combinatorial objects, they are topological spaces where neighborhoods interact. And when these neighborhoods overlap, we exchange information. So that's kind of the topological perspective to look at things. And maybe you have never seen graphs that way. And you can also think of the data we always talked about is just some data we attach to these open neighborhoods. So we go to like the slide I had in the beginning where I was talking about how we model data as simply like something we attach to open sets. this is what we're doing here in the background. Obviously, the combinatorial definition kind of obscures that, but in the background, we have data attached to open sets. So this is how topology allows us to model this very nicely. Now, we also have like an experiment about these long-range interactions, and I'll finish in a second. So we kind of designed this synthetic example where you had to classify the, I think the green node. Yeah, so you had to classify the green node. And we put the label for the green node in the red node, right? So the model had a very easy task, like just go to the red node, fetch the label from there and move it back, right? And once you have it, you can classify it. So it's a very easy task. But now notice what happens when we compare GNN with this cell complex model as we increase the size of this ring. So blue is the GNN and orange is our model. So up to like rings of size, whatever, like 14, like 22. Both models, let's say, do like kind of comparatively similarly, but for rings above 24, so here you would need 12 GNN layers because you kind of need to go like half the length of this cycle. Then the GNN kind of starts to drop dramatically in performance, so you run into troubles. So this is just to illustrate how these things can help. Now, finally, I want to mention that another reason these are useful is that you have some very nice domain alignment with certain applications, and in particular molecules. So molecules have been modeled as graphs for a very, very long time, as Michael was also mentioning, but I think it's time to maybe consider other representations as well, maybe more mathematical ones like this one, and I feel it's very natural to think of these rings as two cells and to model molecules as a cell complex and essentially have a one-to-one matching as before between atoms and nodes and bonds and edges, but now you also have chemical rings and two cells. And turns out that when you use this sort of matching and you can take advantage of all these nice properties I mentioned these type of models have, and you can obtain state-of-the-art results on these data sets. So zinc is a model for predicting the solubility of molecules. Zinc full is just a bigger version of zinc. And MolHIV, for instance, is a data set for predicting, I think is the capacity of some molecules to inhibit HIV replication of something of that kind. And for instance, you can see here this GSN model that also Michael was talking about as kind of counting features and doing things of that kind. So interestingly, when we were not using edge features, these models had the exact same performance. But when we use edge features, our model is actually doing much better. And that's because like it actually updates edge features and it updates all these kind of higher order representations. So it actually, this sort of hierarchical structure seems to be better able to make use of these higher order features. So most graph neural networks just ignore the edge features or never evolve them, whereas we kind of evolve and go through all these hierarchies. So that allows things like the chemical ring to essentially modulate the interaction between the bonds, and then the bonds in turn can modulate the interactions between vertices, but it all comes from the rings. So the rings can also modulate the interactions between atoms. So essentially, you have this higher chain of higher order interactions that allow modeling of the fine-grained relations. So you have this kind of allowing higher order things to modulate kind of more local interactions. And this gives you also some sort of degree of anisotropy. So usually graph neural networks have these isotropic filters, but now you can kind of talk differently to two atoms because they are part of two different rings, and that interaction might be modulated by some other atom on the other side of the ring. So you get all these kind of very nice hierarchies that seem to be the cause for these results. All right, that's all I had to say for this first part. Hopefully I haven't run over time. But yeah, thanks a lot.